Okay, everybody. We are going to start module 15 today. We're just doing part of module 15. We're going to go to example number 2. That will give you a chance to complete all those labs that you have been assigned. So if you had a little bit of trouble finding the materials and you had to order them online, this gives you a chance this week to catch up and do those labs. There are several labs in module 15 too. Look ahead, always look ahead to see what you're going to need for your labs. Module 15 is about electric circuits. So we're going to learn all about electric circuits here, pages 487 to 514. And remember that we're just going to go all the way to example number 2. So here you go. Batteries, circuits, and conventional currents. We're going to learn about that, what it means, definitions, and so on. We're going to learn about resistance and see examples of resistors, like heaters. We're going to talk about electrical power. We're going to talk about switches and circuits. We're going to be talking about series and parallel circuits, so the two kinds that you have. And of course, we're going to put everything in equations, mathematically, how they are related to one another. And we're going to do problems that involve all of the above. We're going to talk about fuses and circuit breakers. And then current and power in series and parallel circuits. So it's all about those circuits and analyzing more complicated circuits. There's going to be some drawing involved in this module. You're going to have to draw, guess what? Electrical circuits. So here we go. This slide just has all the different equations you're going to need to do well in this module. Now, remember that we're going to see each one of them individually, and you're going to learn how to use them one at a time. So don't get scared about this slide. Let's talk about simple electric circuits. This is a simple electric circuit. It includes a battery. It includes a wire. Includes sometimes a switch, usually includes a switch, and then something is hooked to your circuit. In this case, it's a light bulb, but you could have a toaster, you could have, I don't know, you could have a heater, a TV, whatever. You have something hooked to the circuit here. And that is a simple electric circuit. You already know that we make electrons work for us to create electricity, okay? And you already know that those electrons are moving within a wire. I need a wire, a metal wire. Different kinds of metal are better at allowing those electrons to move through them. So usually we use copper because copper is pretty good at allowing those electrons to move. You already know that you can bend the metal into any shape that you need them to bend into, so they can go to different places within your walls, for example, to bring electricity to different parts of your house. Okay. In this simple circuit, the battery creates the electrical field. We learned about electrical fields in the previous module. So we're still doing that. We're still creating electrical fields. The electrical field has the electrical potential that will give us the potential energy that will translate into kinetic energy for those electrons to move. So it's just one more step understanding electricity and how we make it work for us. Here we go. Batteries are rated by voltage. We mentioned this in the previous module. You have seen the little numbers in the battery that say 1.5 volts. Okay, that is voltage. And what does it mean? The voltage refers to the potential difference between the positive and the negative side of the battery. So let's go back for a second. Positive and the negative. The difference in voltage created by this electrical field is your voltage, okay? Your voltage, 1.5 voltage, they have created 1.5 volts of, it's a mouthful here, potential, electrical potential. Okay, here we go. Electrical potential. Mouthful of words here. Okay. A traveling charge, and here we're talking about electrons. From now on, our charges that are moving are electrons, experience a change in electric potential. Yes, which means there is a change in potential energy. You already know that. If there is an electrical potential, you have a change in potential energy. Now, that translates into kinetic energy. You already know that. If the potential energy decreases, your kinetic energy is increasing, and vice versa. Okay? You already know that your potential energy, okay, is related to your electrical potential with this equation. We used it in the last module. We're going to see it again. We might see it again. So here your Q, your charge that is moving, is your electron. From now on, we're talking about electrons moving. The more voltage the battery has, the more work each electron can do for you. Think about it. If this is higher, okay, then that means you have more potential energy. More potential energy, so will translate into more kinetic energy. More kinetic energy, movement of electrons. You need them to move to do work for you, so you can do more work. I hope it makes sense. If it's not making sense, you can always read the book again, and you can always email me, and you can always meet me for a Zoom meeting on Fridays. So here you go. More about electrical circuits. On page 487, I want you to notice that a battery can be represented with this picture right here. Okay, the longer line represents the positive side of your battery, and the smaller, shorter line is going to be your negative side of the battery. Pay attention because you're going to have to draw stuff like this. From now on, a battery is represented with this picture right here. This is a simple circuit because we have a wire connecting the two ends, the positive and the negative. It could be connected to anything you wanted, like a light bulb if you needed to. And you already know that the more voltage that battery provides for us, the more work each electron that's traveling through the wire can do for us. Okay? So let's move on. Page 488. Please be careful here. Electrical current. We're going to be able to calculate electrical current in a minute by using this equation right here. Electrical current is an I. Doesn't make any sense, but it is an I. And is the change in Q divided by the change in T. What does that mean? It means the amount of charge, your Q is going to be your charge, that travels past a fixed point in electric circuits each second. So you have coulombs, that's the amount of charge, is in coulombs by units of time, your second. Coulombs per second is called the ampere. So you're going to put an A. A is abbreviation for ampere. Your units for electrical current are the ampere. So you have here your circuit right here. Here's your battery, long one for the positive, short one for the negative. You already know that the electrons travel this way. You see these electrons travel from the negative to the positive. But when you draw the current, when you draw the I, you're going to have to go the other way. You see these big arrows right here are going from the positive side to the negative side. This is called conventional current. I'm going to have another slide to explain this a tiny bit more in detail. Conventional means that it's always been drawn this way. So we still draw it this way, even though we know that's not the correct path the electrons follow. So the electrons do travel from the negative to the positive, but when we draw the current, we go from the positive to the negative. Okay? And this right here is allowing you to calculate the flow of electrons. How many electrons per second are going through this circuit? Okay, let's talk about this conventional current. Okay, conventional current. You already know that the real electron flow goes from the negative side of your battery to the positive side of your battery. That's how the electrons flow for real. But because we have always done it this way, when we talk about current, okay, when we calculate current, we are going to draw our arrows the opposite way. We're going to go from the positive side to the negative side of our circuit. And here's another example. You see this current right here represented? Current. When I'm drawing my arrows, you're going to be drawing arrows yourself in a minute. I need to put my arrows going from the positive to the negative just because we have always done it this way, even though I know that's not how my electrons are traveling. Okay? If you have questions about this, just ask. This is on page 490. Now, you're going to have an experiment that has current and resistance, but I'll be assigning that a little bit later. Let's talk about resistance. What do we mean by resistance? Well, you already know that when electrons travel through any metal, they're going to encounter some kind of resistance. Some metals are better at allowing electrons to move through them than others. That's why we use copper instead of using a different kind of metal for our circuits that we use for at home, you know, when we're putting an electrical circuit for all the appliances we have at home. Usually we use copper because it's a good conductor of electricity. Not all metals conduct well. Now, it's not only the type of metal that you have to worry about, but also the width of your conductor. Wider conductors conduct electricity better than thinner conductors. You probably have seen that if you look at your wires, they come in a bundle. There are several thinner ones making a big, long, thicker bundle. Okay, you probably have noticed that. Also, the longer the conductor, so the longer this piece of metal right here, this metal, your conductor, the longer this is, the longer the resistance. It has to travel through more metal, so it encounters more resistance. That should make sense to you. Now, we're going to be talking about this right here. This is the way you represent any resistor in your circuit. Resistor meaning anything that you hook to your circuit. It can be a toaster, it could be a refrigerator, it can be your TV, it can be a light bulb. The way you represent that in a circuit is by making these wiggly lines. Okay? These very pointy wiggly lines. So you have resistor 1, a toaster, resistor 2, your TV, resistor 3, I don't know, your heater. So whatever you're hooking to your circuit, those are your resistance. Resistors, which create resistance. The definition for resistance is on page 491, and it reads like this. It's the ability of a material to impede, so it means to stop or resist the flow of charge when it's subject to a potential difference. So you have voltage going through there, which allows those electrons to move. But guess what? That metal will resist the movement of electrons. Some do it better than others. And that's your resistance. I hope this is making sense as well. Ask questions if it doesn't. A little bit more about it is the same information I just gave you a minute ago, but a different picture, a different way of looking at the same thing. Think about electrons squeezing their way through a resistor. So those electrons need to move through the metal. They need to move through whatever you are hooking to the circuit. They have to move through the television. They have to move through your heater, your toaster, your refrigerator. So they all create some kind of resistance. Okay. And here are some more examples, the same examples I mentioned, but you need to know what a resistor is, and you need to be able to give me examples about resistors. Okay. Resistance, the tendency of a material to resist the flow of charges. We talked about these. Friction, they create friction. Heat comes out of that friction, okay? And it can produce light. Now, resistance is measured in ohms. And in a minute, we're going to look at the equation that allows us to calculate resistance. So there you go. Ohm's law. Ohm's law is this right here, okay? The current equals the voltage divided by the resistance. So we can connect all three. Here's a beautiful picture. Remember that your units are going to be in ohms, and it has this shape like a horseshoe. So you have your voltage. The voltage is created by your electrical field. Electrical field is creating a potential energy that allows the current to flow, correct? This current is moving through your wire, but it encounters resistance. It encounters this resistance right here. That's why you see this picture is kind of impeding, stopping the flow of those electrons through the wire. It's kind of a joke, but you need to know the units. Resistance are ohms, your voltage is the volts, and your units for current is your amps, okay? And we're going to be using this in a minute. There you go. Now, pitch 492, another circuit here, another circuit, but here they're showing an electrical heater hooked to it. An electrical heater is nothing but a resistor, and the way you represent a resistor is by the squiggly lines, the pointy squiggly lines right here. Your units are going to be ohms for resistance, and remember that the current is flowing from the positive, this is your positive, longer line, to the negative, even though you know that's not true. And this is your battery provides the voltage, your volts. You're going to have to draw stuff like this. So start memorizing all these kind of pictures. How to draw a battery, how to draw resistors, and how to draw your current. Now, let's put all of this together. Example 15.1, okay? So how do we put all of this together? Let me read the problem. It says a typical space heater has a resistance of 11 ohms. When plugged into a wall socket, this heater is exposed to the equivalent of 120 volt potential difference. Draw a circuit for the heater, you should say the heater, determine the current, and draw the direction of the current flow. So you have to put everything we have learned so far together. Let's start by drawing it. Let me try to go to... I'm trying to go to my... I'm trying to go to my whiteboard, and it looks like I had not pulled it up. So here you go. I pulled it up. So you draw your battery. You start by drawing a battery, the long and the short. You connect everything. You make your system, your circuit right here. You know you have a resistor, so you're going to have to put a resistor in there. You need to close it, okay? Very good. So what do you know? You know that this is 11 ohms. It was given to you. The space heater has a resistance of 11 ohms. We know that. You also know that you have a battery. Well, it's not a battery. You represent it as a battery. You have a wall socket, but a wall socket acts as a battery. And this is 120 volts, okay? So you have something, your socket, your electrical socket, that provides the voltage needed for those electrons to flow. And how do they flow? You know that they go from the negative to the positive, but that's not how you represent it, okay? You represent it going this way. You can put arrows all along, okay? And that's your current. Your current travels this way. You have the first part, which is drawing what's going on here. What else did they ask you? Okay, you already did the current flow, but they also asked you, let's see, to determine the current. How do you determine the current? Well, you have this equation that allows you to calculate the current with only the resistance and the voltage. So use it. You have to modify it. Your current is going to be your voltage divided by your resistance, and you have everything in the right unit, so you don't have to worry about changing anything. It's 120 volts divided by 11 ohms. And if you do that, you should get 11 amps. Okay, you can put amps if you want to, or just put an A. And that's the end of this problem. Example 15.1 is as simple as that. Just apply what we have covered so far, just that. Okay, let me go back to, if I can, yep. Let's start here. Okay. Let me move this over here so it doesn't interfere. I would like you to try extra practice problem number 2. You're going to find those on page 580. So remember what we're doing. You can stop the video here, you try it, check my answer, and if your answer is the same as mine, you don't need to look any further. I mean, you just speed the video forward. You don't need to see how this is solved. So let me change again to my board right here. And for this, I'm going to use yellow. And number 2, the answer for number 2 is 6.9 ohms. 6.9 ohms. So if you got this answer, you're done. You don't have to do anything else. Okay? Let's see. I'm going to read it first, and then we'll see how this is done. Number 2 says, what is the resistance of a wire that can carry 32 amps under 220 volts? Well, let me change color right here. It's exactly the same thing we did before. Your current equals your voltage divided by your resistance. So now you need to modify how this is written, because they're not asking for the current, they're asking for the resistance. So you need R, and R is your voltage divided by your current. And you have everything. The problem gave you all the numbers you needed. That's 220 volts divided by 32 amps. Do the math, and that should give you the 6.9 ohms we talked about at the beginning. Okay, this concludes extra practice problem number 2. Let's go back to instruction. Okay, let's talk about electrical power for a second. That's going to be on page 485 in your book. What is electrical power? This is defined as the amount of work done by an electric current per unit of time. This right here allows you to calculate it. The power with a P equals the voltage times the current. Another way of doing that, if we use Ohm's law, is like this. Just substitute the voltage by the resistance. So you can also say that the power equals the current square multiplying the resistance. You have 2 different equations that allows you to calculate electrical power. And different problems are going to give you different things. So figure out what they're giving you and which one of the 2 equations makes more sense to use depending on what they're giving you. Okay? The units for this electrical power are the watts. And a watt is just the ampere square multiplying the ohms, which is the units that you would get using this equation. Now, for a resistor in direct current circuits, remember that we are drawing direct current circuits. the ones that go from the positive to the negative, those currents. The power is given by the product of the applied voltage and the electrical current, which is what this equation is saying, mathematically saying the same thing, okay? It's the same words or mathematically putting it together in an equation. So let's see how we apply this. Let's see that. Okay, on page 496, we're going to do our last example, and then you're going to have 2 to do that are extra practice problems, and you're going to have a bunch of labs to do this week on this, but let's see. It says, in the previous example, we learned that a space heater used 120 volt wall socket to run and draws 100 amps of current. How much power does it use? How do we solve something like this? Let's go back, get a new page right here and get my numbers in front of me so I'm not copying them wrong, which happens, I can copy numbers wrong. So here you go. What do they want to know? They want to know the power. Okay, I want to know the power here. Which one of the two equations we have that allow us to calculate power makes more sense for us to use? What are they giving us? They are giving us 120 volts and also 11 amps of current. Well, we do have an equation that puts both voltage and current together. It looks like this. Power equals current times your voltage. Well, just put it inside the equation. 11 amps multiplying the 120 volts. Put it all in your calculator and you should be getting electrical power of 1.3 times 10 to the 3 bananas? No, watts. Okay, so don't forget to put your units. The book also tells you, for you to kind of start thinking what that means to have that much electrical power, that a light bulb is 100 watts, okay, or requires 100 watts. So this power is enough to light 13 light bulbs, okay? So just so you understand how this is all related. Very good. Let's go back to the second part of the problem. Let me go back here. So example 15.2, the second part of the example. It says a motor draws 1.19 amps of current and has a resistance of 101 ohms. Assuming that the motor is 100% efficient, what is its power output? Okay, they're asking for power again, don't they? But what did they give us this time? They gave us the current. They gave us the current because they gave us 1.19 amps. What else did they give us? They give us the resistance, 101 ohms. Okay, and we need to use the formula or find the formula if you have it in your formula page or your card of formulas. You would find the formula that connects the two of them. Which one of the two connects the two of them? The one that looks like this. Your power, electrical power, is going to be your current square times your resistance, which is exactly what they gave us. So put those numbers in. 1.19 square, I'm not going to put the amps. You can if you want to, multiplying the 101 ohms. So put all of these in your calculator and you should be getting 143 watts. So your power is 143 watts. Remember that a light bulb requires 100 watts. Now, because this is 100% efficient, the problem says it's 100% efficient, the motor's output is 143 watts, okay? if the efficiency was not 100%, they said 90%, then you would have to find 90% of this number. But they said 100%. So you leave it like that. No problems. Now is your turn. So let me get my mouse and show you what you need to be doing. You need to try these on your own. So extra practice problems 3 and 4, you can find them on page 580. Remember that I'm going to give you the answer first. You find the same answer, move on. But if you don't find the same answer, watch the video to see how it's solved. So let's get started. Let me get my extra practice problems. So let me go back here, a new page. And number 3, the answer you should be getting for number 3, let me get yellow. So the answer for number 3 is, your answer for this one is 220 volts. So if you got this answer, you're done. Move on to number 4. But if you did not get this answer, watch to see how this was solved. Let's read it first. You always read it. Always read it. See what they give you, what they're asking you, and so on. Number 3 reads like this. What is the voltage behind a 15 amp current flowing to a heater that draws 3.3 times 10 to the 3 watts of power? So what did they give us? They give us the current. 15.0 amps equals your current. Okay, remember that. That's your current right there. They also give us this number, 3.3 times 10 to the 3 watts. And in your head, you should make the connection that this is your power. So, what formula are you going to be using that connects the two and is going to allow us to calculate the voltage? Well, this is it. Your power equals your current times your voltage. And from here, you can modify it algebraically and say that your voltage is going to be your power divided by your current. And you have everything you need. You do. So let's get another page right here and put all those numbers in. Your voltage equals 3.3 times 10 to the 3 watts, okay, divided by your 15 amps. And if you do your math, you should be getting the 220 volts we said your answer needed to be. So there you go. If you didn't get this, check your calculations with your calculator, okay? Very good. So let's look now at number 4. New page. For number 4, if you get this answer for number 4, which is 0.345 amps, okay? So 0.345 amps. If you get this answer, you're done. But if you did not get this answer, then check to see how this is solved. Okay. Let's read the problem first. Always read the problem. It says, what is the current? So they want to know the current. This is your question, the current, okay? Of a circuit that has 34 ohms of resistance. They give you the resistance, okay? That's 34.0 ohms. And uses 4.05 watts. So they give you the power, okay? They give you the power, 4.05 watts. What formula connects those two and will give you your current? Well, this one does that. Power equals your current squared times your resistance. This is it. That's what you need to be using. You just need to modify it. Your current is going to be the square root of what? Well, your power divided by your resistance. Solve these because you have all the numbers. You have them all. All the numbers you need are there. So let me get another page and put the numbers in for you. Your current is going to be the square root of 4.05 watts divided by 34.0 ohms. Okay, ohms. And that's where you get the 0.345 amps of current. Okay, there you go. If you have any questions, join me for a Zoom meeting or email me during the week. I'm here to help you. So I hope this goes well. Remember to take this week to catch up on any labs you still need to do. Keep safe, please.